which is mobile networking. So we're going to move up from looking at an example Layer 2 wireless technology, which was wireless LANs, and look at Layer 3 issues with mobility. The first few slides will just explain the scenario that leads to some problems, and then we'll spend some time going through one protocol that attempts to solve a mobile networking problem. The scenario is that let's assume in the near future that, if we turn off that light, in the near future that we'll have access as end users to a variety of different network technologies that provide us ubiquitous access to the internet. Ubiquitous means we're talking about from anywhere, anytime. We almost have, or we have part of that already with our mobile phones. We can use our mobile phones to access the internet, and our mobile phones can switch to using Wi-Fi. If we're home and we have a wireless access point, then that's one part towards this ubiquitous wireless network. But not just using our mobile phone, but using other devices. So connecting all devices together using short-range technologies, connecting people together using wireless technologies, in-vehicle communications, so having internet access while you're inside a vehicle. Again, that's possible via a mobile phone, but other technologies, if you're talking about buses, trains in some countries, then they may use satellite and WiMAX and other technologies. Inside your home, you have your Wi-Fi access point and it provides service to different devices. Between homes, in some cases, if you want to form a network amongst homes. Between vehicles, so not just for you inside the vehicle to access the internet, but for vehicles to communicate with each other on the road to provide initially safety applications. If there's an accident, to let some vehicle know. So it either gives you a warning, a visual warning inside the vehicle, or it actually controls the vehicle in some way. So the idea is that we can access internet services from any location at any time using any device that we have on us. And not just using one wireless technology, not just using 3G, not just using Wi-Fi, but whatever is the most appropriate for that location and time. We can do part of that today, but there's a few things missing to make that seamless from the user's perspective. Some assumptions that we're going to make. First, we're going to assume that all of our communications we want in this future network is IP-based. So that's typical with our internet access, our data access, but also our voice access. And TV. Let's assume that everything that we access when we make voice calls is using voice over IP. Same with video calls. The delivery of TV to our mobile devices is via the IP network. And other services and applications, let's assume that they're all via IP network. And we're getting close to that now. You can now make voice over IP calls with your phones. You can watch voice over IP, video or TV over IP in some networks. Another assumption is that the user wants unrestricted access to the communication media anytime. So I think that's well understood. We're going to assume that cities at least have coverage for different wireless technologies, and normally more than one technology. Mobile phone networks provide coverage, Wi-Fi or wireless LAN hotspots provide coverage, and there may be other technologies that provide coverage where needed. WiMAX as another alternative, in some cases satellite. As a user, I like to have my device or devices and to be able to get internet access via any of them, the best one possible. And not always the case in some countries, in most cases, that there are multiple network operators. That is, there are different companies that will offer to provide these services to me. Not just one company, but I would choose the company that best suits me based on financial costs, based on what they deliver as a service. And sometimes I may subscribe to multiple operators and be able to switch between them as I choose. Some scenarios, and we won't go through any detail, but some scenarios where such assumptions will benefit if we have home area networking, connect all our devices via wireless and wired technologies inside your home, personal devices, entertainment devices, control, air conditioning, lighting and so on, appliances in some cases. And we can do this to some extent now already. That is, most devices, or you can buy devices that you can, for personal entertainment control, that run over IP networks inside your home. If that device talks IP, that is, it has software or hardware that supports the internet protocol, then we can use most of our common applications, and it's not hard to program an application to communicate with it and control it. Another area is networking between vehicles, so allowing people inside vehicles to get internet access, and also allowing exchange of information about the vehicle to the user, like fuel level, speed and so on, and exchanging information between vehicles. So we can provide safety type applications across across a highway, where a vehicle will get a notification if there's an accident 5 kilometres ahead, and that will either give a visual warning or some automatic control of the car. And there are other scenarios where having a ubiquitous wireless network is of benefit, and some of them are available today, but in the future there's some new things needed to make them usable and seamless from the user's perspective. So what enables these scenarios? What do we need for these scenarios to work? We need good wired networks, although most of them require the end user has wireless or mobile access. Still, we use wired networks to connect the base stations and so on. So we need good, fast wired networks, and that's generally available today. We need good wireless network technologies from the perspective of the physical and data link layer. That is, high speeds, high data rates. And again, they're available or becoming available today. That is, we can get download rates of tens of megabits per second, which are the types of rates that are needed to support things like video over IP, high quality video. The thing that we're going to focus on in this topic is providing internet mobility. That is, the ability for you to move between different subnets, IP subnets, without having to lose your connection. So we're going to spend some time explaining the problem there, and it's about allowing a host, your mobile phone for example, to move between different technologies, between a Wi-Fi access network and a 3G access network, or within the same technology, maybe between different operators, move from you using 3G from AIS and you also subscribe to another operator. You'd like to be able to move, physically move, and use the best network available for the best price. And you want to do that without interrupting your communication service, without having to stop your voice call or your download. And when we're using IP, there's a problem with that. And that we'd like to be able to move without having to change our IP address, host mobility. In some cases, we'd have an entire network that moves. If you think about a car, there may be multiple people on board the car with their devices. The car may have some devices using IP, so we have a whole subnet inside that car. And the car is moving, so that network is moving. So we need some mechanisms to provide network mobility. We'll mention them as well. Host and network mobility. Other things that may be useful to enable this ubiquitous wireless access is ad hoc or infrastructure-less networks. Not connecting from your device to the access point, but connecting from your device directly to another device. Okay, you can do that today. You can create a ad hoc link from my laptop to someone else's laptop. Don't need the access point. But now let's create a link from my laptop to someone else's laptop, and then to someone else's laptop and another one, and form a network amongst them. That's the topic of ad hoc networks, or infrastructure-less networks. You don't have access points or infrastructure pre-built. Good in cases where you don't have the infrastructure available, or you need temporary networks. You just want the network to start within seconds, as opposed to relying on some infrastructure. If we get time, there's a few slides on ad hoc networks. We may mention them briefly, but not in much detail. What else do we need? We need good applications and protocols that support these things, and some of them are available today, like voice applications, video applications. We need devices that support multiple wireless technologies, again, available with most mobile phones today. Most mobiles will support different mobile phone technologies, 2G, 3G at different frequencies, Bluetooth, wireless LAN, and in the future, and some already do in the US, for example, in Europe, WiMAX. So most mobile phones or handheld devices will support multiple wireless technologies, allowing you to switch between them depending upon your needs. If you're home, use the Wi-Fi. When you leave your home, switch automatically to 3G. Those devices need to be energy efficient. We want to have them last as long as possible on the battery and have good applications and user interfaces. And there are a number of other things that we need to support this ubiquitous mobile access, security, quality of service, and so on. We're just going to focus on one thing, and that's about mobility issues. Mobility at layer 3, at the IP layer. How do we support that? So today we'll go through, start on host mobility. And if we get time, maybe next week we'll talk briefly about network mobility and maybe even ad hoc networking. And host mobility, we'll see that there's a protocol called mobile IP, or generally called mobile IP. It allows you to be mobile and maintain your IP address. And we'll see why we need a new protocol to enable this. Why can't we do it just with normal IP? So referred to as IP mobility, or more generally mobile IP. And we're talking about host mobility as opposed to network mobility. Host refers to our end user device, our laptop, our mobile phone. Mobility can be physical mobility, but we'll see it doesn't have to be physical mobility. That is, we'll see that, okay, if I move with my mobile phone, I'm mobile. Okay, that makes sense. But sometimes I may be standing in the one position. I may have the choice of using Wi-Fi, 3G from one operator, or 3G from another operator, without moving. And sometimes, under different conditions, I may want to switch between them. That's considered host mobility. I'm not physically moving, but I'm moving my network attachment. We'll see how that works. First, to understand why we need this new protocol called mobile IP, we need to make some assumptions about our network and our underlying layers. First, we need to distinguish between layer 2 and layer 3 networks. As a reminder, our typical internet stack our 5-layer internet stack from the physical layer up to the application layer. Layers 1, 2, 3, 4, 5 from the bottom up. Layer 3, we are normally assuming we're using the internet protocol. That's the protocol used at layer 3. At the data link layer and physical layer, which generally go together, then we have a variety of different technologies. The last topic, we went through one example. Wireless LANs is one example for our layer 2 technology. But there are others, 3G and so on. So here's layer 2. We need to distinguish between wireless access and mobility in a layer 2 network compared to a layer 3 network. Here's an example, and we use wireless LAN for examples in this because we know how it works from the previous topic. Here's an example where we have some IP router, and on the other side of that router, although not shown, let's assume there's the internet, and a single IP subnet where we have a switch, an Ethernet switch, some wired links here to 2 access points, and we have a number of hosts associated with those access points. Mobility, if we look at layer 2, which is just inside this network, then we can use the layer 2 mechanisms to be mobile in here. That is, host x.a is associated with this first access point, the top access point. As it moves, then 802.11, the wireless LAN, has mechanisms for it to hand over to the new access point. That is, it associates with this one. As it moves, it makes a decision. Okay, I want to use the new access point. I will reassociate with this new access point. So there's some messages it needs to send, some frames it sends to perform that handover between the 2 access points. That's what we call layer 2 mobility. It's mobility just within this one IP subnet. It uses the mechanisms built into the layer 2 technology. That is 802.11 in this case. The same with your mobile phone within a 3G network. That is, there are many base stations. As you move, the 3G technology has mechanisms such that as you move, you can switch between the different base stations. It deals for that mobility for you. But from the perspective of the internet protocol, you're still within one IP subnet, and that's key here. We'll see, and we'll use this throughout these slides, is that to simplify the IP addresses, I'll just break them into two letters, where the first letter represents the network portion of the address and the second letter the host portion. For example, on my laptop, my IP address, and this is a hard example, but we see my IP address 10.10.99.251. In the examples that we'll go through in the slides, instead of using the full IP address, I'll say, okay, the IP address consists of some value that represents the network and some value that represents the host. And we tell that from the net mask. So in this case, the mask is 255.248.0. So the network address is 10.10, what's 99? That's a hard one. I think it's 96.0, and the host portion is the remaining bits. Remember, if our IP address, we have 32 bits. The first set of bits identify the network, the remaining bits the host. And the net mask tells us where the split is between the network and host portion. Rather than working with real IP addresses, I'll just use letters. X, the uppercase X here refers to a network. D refers to a host within that network. So this is one IP subnet here. The router has an IP address on this side, x.z, and the 4 hosts have IP addresses, A, B, C, and D, in the subnet X. So we'd refer to this subnet as subnet X, for example, in our internet. And there may be more subnets over here, Y, A, B, C, and so on. The point is, in layer 2 mobility, as the host moves, it's within the same subnet. This x.a moves to the second access point. It's still x.a. It's got the same IP address. It's in the same subnet. It's still in subnet X in this case. So mobility within the same subnet is handled by the layer 2 mechanism. Mobility within wireless LAN access points is handled by 802.11. But when we need to be mobile between different subnets, that's when different challenges arise. If this mobile device x.a wants to move to an access point which is attached to a network out here, network Y, for example, then it can do the layer 2 handover, but we have a problem in that we now have to somehow change our IP address, because we have some rule that any host in this subnet must use the network portion X. So if we move to a subnet Y, we'd need to change our IP address from x.a to y.something. We'll see that that's a challenge. So we're not talking about, from now on, layer 2 mobility. We'll be talking about layer 3 mobility, IP mobility. We'll assume that any of these layer 2 technologies could be used, but we'll use examples mostly from wireless LANs because we understand that the most. So to simplify that single subnet, we may draw it like this. There's a router and there are 4 hosts. I've hidden the access points and the cables in here and the switch just to hide that details and make our discussion simpler. And we'll refer to this as an access network. It's a network where the hosts access to the larger internet. So beyond the router, maybe other subnets and the internet. So we don't care at this point how these hosts connect to the router. It can be via Wi-Fi, it can be via 3G, any technology. We don't care for this discussion. And our rules are that, and these are just normal rules of IP addressing and IP networking, all hosts or all devices inside one subnet must have the same network portion in their IP address. This router, the 4 hosts, must be x.something. And the host portion must be unique, A, B, C, D, Z, for example. That's our normal IP addressing rules. And of course we may have access networks, multiple access networks, and let's say they connect together via some core network. So here's an example. We have 3 access networks which are similar to this, which may have hosts in them, and each have a router. And in fact those routers have a second interface, 2 or more interfaces, connect to some core network which makes up our entire internet. We'll use this type of setup in our examples to explain mobile IP. We don't care how, in fact, we send from here to here, whether it's a wired network, whether it's across the globe or it's across a city. It's just some IP network where we send an IP packet and it will be delivered via normal IP forwarding mechanisms to the destination. So, what's the problem when we move between subnets? First problem is that in the internet depends upon having address. Each node or each host has an address that fits the format of the subnet that it's in. And the routing depends upon the addresses. That is, here we have host x.a and b in subnet x. If host z.a over here wants to send an IP datagram to x.a, then it creates the datagram, and in that datagram will be the packet header and include the source and destination addresses. Here's our IP datagram. It has an IP header and some data. And this is what host z.a wants to send to, say, x.a. In that IP header, there are a number of fields, two of them of interest: the source address and the destination address. What's the source address? What's the source address in this IP datagram? Again? Z.a. It's coming from host z.a. So our example, this one wants to send some data to here. The source is z.a. And the destination? We want to send to this host. What's the destination? x.a. Note that the destination is the final destination. It's not the intermediate router. It's the final destination. Okay, that's our normal IP datagram. How does that datagram get to x.a? Well, we use our routing tables. Z.a looks up the routing table, which should tell it what is the next device it needs to send to. That is, what is the router that it needs to send to. How are these routing tables created? They are created by running some routing protocols. Let's first draw an example routing table for z.a. where we simplify the routing table as just two columns. What is the destination that we want to reach? And to reach that destination, what is the next hop we want to send to? So a simple routing table for Z.A may be just one entry. Destination star, meaning any value. Any destination I want to send to, the next hop, the next device, is Z.Z, this router. Anytime this host wants to send an IP datagram, doesn't matter who they want to send to, x.a, y.e, anyone, they'll send to the router. What about the routing table of that router? Although our diagram doesn't show it here in the internet cloud, there may be many routers in here. And the routing table for router Z.Z would be constructed such that to reach our destination, let's say subnet X, x.star, anyone on the X subnet, maybe, although we don't have it, maybe there's another router, the next one along, which is router A. Not shown on our diagram. Let's say there's another router here, router A, and then that router A would have routing table would say to reach network X, send to router X.Z. So the routers in the internet would have routing table entries saying to reach some destination subnet, subnet X, send to the next router. And eventually they should be configured such that the next router will eventually be X.Z. One more routing table. This is nothing new to us. This is what we've covered in last semester in IP and ITS413. Will be a bit more complete. Destination next node. Let's say there was some router A.A in the middle, and that was connected to X.Z. Then it would have an entry to reach X.anything, subnet X, send to X.Z here. What about X.Z? What would its routing table entry be? Or one of them at least. If we're considering the packet that needs to get to host X.A, what do you think router X.Z will have in its routing table? Again? What's the destination? Or one way we can think of it, once the datagram gets here, if the destination is anyone on this subnet, we can write it in different ways, but I will say simply direct. It's once the IP datagram gets to here, the destination on subnet X is directly attached from the IP network's perspective. That is, they're on the same subnet. So that means when the router receives the IP datagram, the destination of this IP datagram was X.A. When the router receives that, the router is on subnet X. So now it knows it needs to send using the layer 2 technology direct to that host. So we would use our wireless LAN, for example. If this was our wireless LAN network, it would, or the Ethernet and the wireless LAN, it would find the MAC address of X.A, create an Ethernet frame and send that, which would be sent across the wireless link and eventually be received. So when we say direct here is the next destination, it means we use whatever layer 2 technology is available here. But from the IP network's perspective, it's just a single link. We have a direct link there. That's normal IP networking. How are these routing table entries created? Some routing protocols were running on the internet. More generally, or actually more specific, we have routing protocols inside autonomous systems and between autonomous systems. But routing tables were running that created these entries to find the shortest paths between, or the least cost paths between source and destination. And importantly, the routing is based on subnets. That is, Z.Z stores an entry for subnet X, not for X.A or X.B, just for subnet X. It's only router X.Z that stores information about the hosts in here. Everyone out here doesn't care about the hosts inside here. They just care about a route to reach this subnet. So we have routes to reach individual subnets, and then that router deals with delivering to the final destination. That's where we see this X.Z as X.star as the destination, meaning if we want to reach anyone on subnet X, send to this next router. So that's how IP routing and forwarding works today. What's the problem? The problem is when our host moves between subnets. My laptop has moved, it's physically moved. We now no longer have coverage within the wireless LAN here. We'd like to connect to the 3G network, which is provided here, so that I can continue accessing the network. So I move here. What do I do with my IP address? Well, I change my IP address. Otherwise, the routing will not work. Because if I move here and I keep my IP address as x.b, and now ZA sends me a datagram. Destination, sorry, I keep my address. All right, here's x.b in the diagram. Let's say x.a moves. I keep my address. I've moved. Z.a is on the other side of the world. He doesn't know I've moved. Okay, so he still sends an IP datagram with a destination address x.a. The routing tables are the same. The routers don't know I've moved. Possibly this one does. This one says, okay, destination x.a, send to a.a, a will send to z. The IP datagram will be forwarded to this subnet, but I am in a different subnet. I'm not going to receive the datagram. So this router would receive it, and it cannot send the datagram to me because I'm not attached to this network. I'm no longer in this network. So if I move to a different subnet and I maintain my original IP address, then the routing will not work as we know it in IP. So what do we do? What's your idea?
Forward to another subnet.
Forward to another subnet. Good. If it gets here, then somehow we need this one to recognize that I've moved and forward it to this subnet. And that's what mobile IP does for us. What's another option? The other option is to change my IP address. That is, I'm x.b, I've moved to this subnet y. When I join this subnet, get a new address, y.b. But of course, that creates a problem in that this device no longer knows my address. Applications or application sessions depend upon IP addresses. Most internet applications using TCP create a connection depending upon the source and destination address. When you're downloading a file, then that application depends upon that source and destination being the same. If I change my address during a download, normally that means that the application session will end. It'll stop the download and have to restart. So most applications depend upon fixed IP addresses. So interrupting or changing an IP address, changing from x.b to y.b here, is possible technically, but if I'm in the middle of some data transfer with Z, it will no longer be able to send me data. You'll have to interrupt that connection and start again. For example, in the middle of a voice call, that call will drop and we'll have to restart the voice call. So changing the IP address is not an option either because it interrupts the application. We would like to be able to be mobile and from the user's perspective, that mobility to be seamless. That is, I don't notice it. I'm on my mobile phone, I'm talking to someone, I'm connected to the Wi-Fi network, I move a little bit, Wi-Fi is out of coverage, it seamlessly hands over to the 3G network without me noticing. That's what we want. If we change the IP address, that's not possible in general. Changing the IP address normally means we need to restart the session or the application data transfer. This is okay for what's called being nomadicity. That is, you have your laptop here, When I moved back to my office, I shut down and reopened my laptop back in my office. Getting a new IP address in that case is okay. But for true mobility, I'm walking and I want continuous access as I walk. It's not okay to stop the session and restart again. Mobility should be seamless. Seamless from a user's perspective and an application's perspective is maybe there's small delays of tens of hundreds of milliseconds between this handover, but not much more. If there are larger delays, then the user notices and the applications may not work correctly. So we cannot keep the old IP address because routing will not work. We cannot change the IP address because the applications will not work. So the suggestion is, and that's the answer, have our router forward data to us. So the solution is to change the IP address, but to hide that change from the applications, the transport layer and the applications. Essentially get two IP addresses. Our original one and a new care of address. And that's what's implemented in mobile IP, which is an IETF standard. So we'll go through how this works and the different mechanisms for IP mobility. So that was about the motivation for IP, that if we for mobile IP. Sorry, if we want to be mobile, our normal IP routing and IP address structure does not work for us. So we need something different. So that thing different is called mobile IP. There's some RFCs, there's some standards that define how it works. There are many extensions to improve it from the perspective of security, improving performance. You've studied mainly IP version 4. Maybe in Dr. Comwit's class you're studying IPv6. We're going to talk about IP version 4 when we talk about mobile IP. But the same concepts apply in mobile IP version 6. So if you understand one of them, you understand both. There's some small differences, but the same concepts. It's optional. That is, my laptop doesn't support mobile IP. I need to install some software to get that support. So most operating systems, you can get support, but may not be enabled. In mobile IP version 6, it is built into IPv6. That is, if you have IPv6, then you have the basic features for mobile IP version 6, especially in routers. So we're going to focus just on mobile IPv4, but the same concepts apply with version 6. This is the basics of how it works. Here we have host x.b wants to move into subnet y. That's the scenario. That's mobility. So we have our host that we're communicating with. What's this second blue one? Okay. Actually, we're going to see that we move from subnet x to y and eventually to subnet z. Let's start in the first move. What we do is we have our normal IP address, x.b. When we move into a new subnet, we get a new second address, a care of address. So we can now think our mobile host has a home IP address, the original one, and when it's away from its home network, we get a care of address here, for example, y.m. So now we have this concept of home networks and foreign networks. For example, my SIT laptop, the home network will be within SIT's subnet. When I move outside, then I'll be visiting a foreign network. In my home network, I get an allocated IP address. When I move to any other network outside of SIT, I would get a care of address. So let's say this is the home network for host x.b. When it moves into subnet y, it gets a care of address matching that subnet. And if it moves again into subnet z, it gets another care of address corresponding to the subnet that it's in, z.t. So that's the concept. And if that works, we'll see how do we deliver data, let's say from z.a to x.b. When the host is in its home, normal IP data delivery from z.a routed to x.b. When host x.b moves into a foreign network, z.a doesn't know that. It's hidden from the original, or from z.a. So it still routes the packets through the internet to subnet X. So somehow we need to tell the router here that x.b has moved. It's no longer home, it's now in the foreign network Y. And this one will forward the datagram to subnet Y. We'll see that in some examples. Do we have any other terminology here? So we have nodes or hosts. Nodes can be either mobile, they support mobile IP, or the other nodes we'll refer to are the correspondent nodes. They're the nodes we're corresponding with. For example, z.a is the correspondent node, the one that we're communicating with. So here's our mobile node, here's the correspondent node. They are sending datagrams to each other, corresponding, and as the mobile node moves, we update its care of address. So every node has a home network, a single home network now. So where you get your original IP address, that's your home network. So you get an IP address from that home network. From that node's perspective, all other subnets in the world are foreign networks. So we have home networks and foreign networks. And we have two new entities in our network. One's called a home agent and the others are foreign agents. We see for host x.b, its home network is subnet X. On that subnet, there's some home agent. A home agent does things on behalf of the home mobile nodes. It's typical for the home agent to be running on the router in that subnet, although it doesn't have to be. It could be a separate host. But in our examples, we'll consider it a router. That is, this router is the home agent for x.b and x.a. And we also have foreign agents. Again, we'll use them as running on routers. A foreign agent handles activities for nodes that move into the foreign network. Do we have another diagram? Possibly, if my computer will respond. The previous two slides have some of the terminology, but we'll use this diagram here to illustrate and mention the terminology. So here's coming back to our case where correspondent node z.a is corresponding with our mobile node x.b. They're sending datagrams to each other. Maybe it's a voice call. They're in the middle of a voice call. And x.b has moved to a new foreign network, subnet Y. What happens is that when x.b moves into this foreign network, it gets a care of address. In this example, y.m. A care of address which matches the structure for that subnet. Subnet Y, y.something. How does it get a care of address? Well, it could be assigned by the router here. But it gets a care of address. Correspondent node Z.A doesn't know about the mobility. If they're on the other side of the world, they don't know who they're communicating with is mobile. So we follow the blue line here. Z.A is sending datagrams to, we've changed our example, to X.B. They're being sent to the first router across the internet. These routers don't know that the host is mobile, and they will deliver that datagram to this router X.Z, because the typical IP routing will deliver a datagram destined to X.B to the router for subnet X. This router receives the datagram, but this router is also a home agent. And the home agent does some special things, and in this case it knows that our host has moved. The home agent knows that host X.B has moved to subnet Y. And therefore it recognises, okay, X.B is not home. X.B is in subnet Y and has care of address Y.M. I will forward that datagram to subnet Y. It will go to the router Y.Z, which is the foreign agent. The foreign agent knows that X.B is visiting its network and will deliver the datagram to the host with address X.B or care of address Y.M. So that's the basic approach there. Yep.
How does home agent handle the forwarding? Like it modifies it routing table?
So how does the home agent here handle the forwarding? So when the IP datagram arrives at the home agent, everything is normal, and then suddenly it needs to send to a different address. We'll see it uses the concept of tunneling. It puts that IP datagram inside another IP datagram. So the destination address, as we see, is X.B. We'll see a detailed example, but it takes this and puts it inside another IP datagram, adds a header on, and sets the source and destination such that it will be delivered to this subnet. And when this one receives it, it removes the outer IP header, and we've got the original one back. So we use tunneling to do that. We don't need to modify the routing tables in that case.
How did the host agent, the home agent know that where did the basically?
Good question. How does a home agent know the mobile node is here? Then, and we've skipped over that, we need some way that when a mobile node moves, it needs to register back to its home agent. Okay, so that's the detailed step that we need to go through. That is, X.B moves to here. Once it knows it's in a new foreign network, it needs to tell its home agent, I've moved to this position.
So X.B had to tell home agent that?
Yeah, X.B will need to tell the home agent, I've moved, I'm now have care of address Y.M. Please deliver the packets to this subnet. Same as you can do it with your mail. You have your home address, someone sends you post. If you're temporarily going overseas or moving houses for 6 months, then you can tell the post office that I have this care of address. Any mail that comes to my home address, please forward it to this new address. So it's just forwarding on behalf. So for that to happen, we need to tell the home agent to do that forwarding. We'll go through how that works, that registration process. What have we missed here? Now, that's in the direction from the correspondent node to the mobile node. So this is showing the data delivery. Sending from the correspondent node to the mobile node goes across the blue path. It goes from the correspondent node across the normal route in the internet to subnet X, and then across this new path from subnet X to subnet Y, and then to the destination. Whereas in the opposite direction, when the mobile node is sending to the correspondent node, it can send to the local router and then deliver direct across the least cost path in the internet to subnet Z. We don't need to go through the home agent for the opposite direction, because the destination address when this one sends a datagram is Z.A. Doesn't matter that our source address is different from where we originally were. The destination is what matters for routing. The destination is Z.A. We send it to the router. To reach Z.A, send in this direction until it reaches subnet Z. So we get what's sometimes referred to as triangular routing. In one direction, packets are routed via the home agent, in the other direction, direct. What's the problem with this approach? What's our problem here?
Overheads, because we have to register back and forward it.
Overheads, because we need to register, so there needs to be some process of telling them that we've moved. And I think the other thing is we need to forward, and in particular we need to forward to the home agent and back. That is, this is the direct path, the least cost path, the red path. The blue one is not a direct path, or not the least cost path. It goes via some intermediate node, the home agent. We need to do that for it to work, but that can lead to performance problems. Especially if going to the home agent and then to the subnet here is a long way away in terms of distance or in terms of delay. That is, the delay can be quite high for our datagrams. We'll see some more examples of that later. Have we missed anything? So we have nodes, mobile and correspondent. We have a home network and a foreign network. A host has its own home network. All other networks, subnets, are foreign. Every home network has a home agent, a special device that participates in mobile IP. Normally we'll assume that they're just routers on that home network. That home agent maintains what's called a mobility binding table. For its own mobile nodes, it records their current care of address. That is, our home agent x.z has a table, some data structure, that records when x.b is moved to here, what its care of address is. So it knows that it's y.m. How does it know? We need to do some registration to tell it. But a table that maintains a list of where are its home mobile nodes at this point in time. Are they home, or which foreign network are they in? We have foreign agents, and they keep track of the mobile nodes that are visiting their network. So they provide addresses when a node enters the network, and they perform the forwarding on the behalf. And they maintain a visitors list, the set of mobile nodes that are visiting, and some details about their addresses. Their home address, their home agent, and their layer 2 address, their MAC address, for example. And we'll consider them implemented as a router, on a router. And we have two types of addresses. Just normal IP addresses. Mobile node has its home address, which is always the same, it doesn't change, and can be assigned a care of address, COA, which is assigned when it visits a foreign network. Again, the normal structure of an IP address, but the care of address is within the range of the subnet that it's visiting. In some cases, now what care of address is given to the mobile node, it can be that we give the mobile node a care of address which matches the subnet that it's in, or we can give the mobile node a care of address which is the same as the foreign agent. We can reuse the same IP address in this special case. In this example, foreign agent is y.z. We gave the mobile node a care of address y.m. Alternatively, we could have given this the care of address y.z, the same as the router. That would work as well. Because what would happen if the care of address was y.z, the datagram would be forwarded to this router. This router knows that this is a special case and can deliver to here. So there's two ways there. Either use a unique address for the care of address or use the same as the foreign agent. So how does it work in detail? We need to register. When we visit a foreign network, we must inform the foreign agent of that foreign network and inform our home agent. Tell our home agent that we've moved into this new network. So this is the mobile IP registration procedure. But before that happens, how do we know that we're in a foreign network? I've moved. How do I know I'm in a particular foreign network? I must discover a foreign agent. So there's a procedure for mobile IP agent discovery. We'll go through that. Another issue is how do we forward the datagram? So the question was, how do we get the datagram from the home agent to the foreign agent? We use tunneling. So there's a procedure for mobile IP tunneling, which we'll go through. We may move between multiple foreign networks. I'm attached to one foreign network, I change to another. How do we handle this? So we need to again inform our home agent, and we may inform the old foreign agent. So there's a process of mobile IP handover that we'll go through. And sometimes we can have extra processes to improve performance. We said that in this case, sending across this blue path is this potentially extra delay. So how can we minimise this delay? And there's some optional features called route optimization and handover smoothing. We'll mention them briefly. Any questions? Ready for your quiz? The concepts are reasonably easy, but we're going to go through in detail how the individual mechanisms work. Start with registration. How do we tell the home agent that we've moved into a foreign network? It's reasonably simple. First, so the example is, if we go back, if it works. The example is our mobile node has moved into this foreign network. It needs to perform some registration. How does the registration work? First, the mobile node needs to discover which foreign network it's in. And we'll go through how that works with agent discovery. That is, we need to know who is the foreign agent. So there's a process called agent discovery. Once we do that, once I know I'm in a foreign network and I know the foreign agent, there's a special registration request, a mobile IP registration request, a special type of packet that we send, and we see the steps. We send the registration request to the foreign agent, saying I want to join your network. And in that registration request, we need to indicate our home IP address. And we're sending it to the foreign agent. So source is home, destination is the foreign agent address. And the registration request contains the IP address of the home agent. So I send a message to the foreign agent and I inform it who is my home agent. Then the foreign agent sends a registration request to the home agent. So the foreign agent, when it receives the first registration request, it says, okay, this mobile node wants to join my network. It can make a note in its visitors list of that there's a new mobile node visiting its network. It can allocate a care of address and then send a registration request to the home agent, which includes the allocated care of address. The home agent, when it receives the registration request, can perform some authentication. We want to make sure that this is in fact a home agent here. It's not something pretending to be a mobile node related to this home agent. So there's certain authentication or security mechanisms that are needed for this to work. If everything's okay, the home agent updates its mobility binding table. The mobility binding table keeps track of the mobile nodes and where they are, and returns a reply, registration reply to the foreign agent and eventually to the mobile node. And once the foreign agent receives the reply, it finalises its visitors list, confirms that everything's okay, and forwards it to the mobile node. And now the mobile node has its care of address and can start sending and receiving datagrams. So once the registration is complete, then the mobile node is in the new foreign network and can deliver IP datagrams, send them out and receive them in. So quite simple process. Register via the foreign agent to the home agent and get a reply back. One of the problems that arises is normally, from a security perspective, a router, if it receives an IP datagram from a source address which is not on its subnet, it will just disregard that datagram. So, for example, here's the SIT router. And the SIT router, let's say the subnet is 72.16.1.0 /24, meaning the subnet mask is the first 24 bits of the network portion. Let's say that's the SIT network. This router, when it receives packets and forwards them out to the internet, often will do some security check. If this is a host and it has the address 72.16.1.3 and sends a datagram, the router checks the source address, 72.16.1.3. It matches the subnet address, everything's okay. If we have some other host which sends from address source address 3.4.1.6, sends to the router, often the router will be configured to drop that packet because it's coming from a source address that does not match our subnet address. It could be some malicious user doing something bad, that is pretending to be coming from SIT's network and performing some attack on some host in the internet. Every host within this subnet should have the address 72.16.1. something. If it doesn't, the routers would be configured to disregard those packets, a security mechanism. That causes a problem with our foreign agent, because if this is our foreign agent, if this is our mobile node, which is visiting, in the registration, our mobile node has moved into here. It's got address 3.4.1.6. It sends a registration request here to the foreign agent. Well, the foreign agents are configured to accept such packets. If it's a registration request coming from a source address that doesn't match the subnet address, we'll allow that through. So there's some extra thing that the foreign agent would be configured to do. Don't drop the packet if it's a registration request only. If it comes from some strange source address, then process it and send it on. So, mobile IP registration happens when we visit a foreign network. Register with our home agent via the foreign agent. But when we visit a foreign network, we need to know who is the foreign agent. We need to discover the foreign agent before this happens. How does mobile IP agent discovery work? How does a mobile node know the IP address of the foreign agent? When it first powers up, that is, I turn on my laptop, I'm in some foreign network. How do I know the IP address of the foreign agent? That's one question. Or when I perform a handover. I'm moving in a car, I'm walking, I'm in my home network. All of a sudden I'm out of my home network, say not within range. I want to use a foreign network. How do I know the IP address of the foreign agent? That's what agent discovery is about. 3 options. There's IP level advertisements. The foreign agents periodically send out advertisements saying, I am a foreign agent. Route advertisements or agent advertisements. So an agent broadcasts periodic advertisements that indicate its own IP address. There are special types of packets for doing this called router advertisements, and they carry information necessary for mobile IP. So that I turn on my laptop, there's some foreign agent nearby. If it's periodically sending advertisements, I'll eventually receive an advertisement and I've learnt the foreign agent. So that's the one approach. We must configure to limit the rate at which advertisements are sent so it doesn't create too many packets on the network. So the default may be 1 per second. The other approach is that when I turn on my device, I perform a router solicitation. I broadcast a message saying, where is the foreign agent? And if there's a foreign agent present, then it will respond with it may respond with a router advertisement. So there's a router solicitation message that the host sends looking for a foreign agent. And usually there's a limit as to how many you can send per second. And when a foreign agent receives a solicitation, it should respond with an advertisement. These 2 concepts are the same concepts as we use in wireless LAN to discover an access point. To discover an access point sends out periodic beacons, and or you send a probe request and you receive a probe response. Same concept, but different implementation. The router sends route advertisements periodically, and or you send a route solicitation hoping a foreign agent will receive and respond. Let's give it have we got time? An example. We'll have an example later of that. Let's just explain the concepts. So there are two approaches for discovering the agent. The other approach is that you use the layer 2 mechanism. This is a special case, really. Maybe the layer 2 technology can be modified to support mobile IP advertisements. That is, we use the wireless LAN beacons. Let's say the access point sends a beacon. If that beacon contained the IP address of the foreign agent, whenever I receive the beacon, I learn about the foreign agent. So that's what's called layer 2 supported techniques. Use the layer 2 technology to learn about the foreign agent. That requires the layer 2 technology to understand IP addresses. That is, for example, modify the beacons sent by access points to carry the foreign address, a foreign agent address. That's possible. So, we discover a foreign agent, we register with our home agent via that foreign agent, and then we have a care of address. The next thing is tunneling. How do we deliver packets from correspondent node to mobile node when it's in a foreign network? Let's see what else we have. These slides have some big pictures in them and they're very slow. Let's just wait. We're trying to go back a slide. Come on. Okay. So now, how do we deliver the IP datagrams from correspondent node to mobile node? Correspondent node, Z.A, doesn't know anything about the mobility of X.B. They've been communicating, maybe they're in the middle of a voice call, voice over IP call, so they're sending packets in both directions. We're looking just in the direction from correspondent node to mobile node. So the IP datagram, I've simplified it here. There's some data, there's a header, two fields of importance in that header, the source and destination address. So the datagram created by Z.A and sent by Z.A, source address Z.A, destination X.B. That's normal IP address or IP header construction in by the correspondent node. Sends that to the router uses its routing table, delivers across the internet. We want to get this datagram to X.B. And eventually it will be delivered to the router for subnet X, which is our home agent. This is where the tunneling happens. The home agent knows that X.B is no longer home. It's visiting subnet Y. It knows because of the registration. The information is stored in the home agent's mobility binding table. So if this home agent receives a datagram where the destination is an address that's in the mobility binding table, then we need to do tunneling. So how does tunneling work? We put that datagram that we received inside another datagram. The datagram received data and an IP header. So that's the original datagram received by the home agent. What we've tried to illustrate here is we take that and put it inside another IP datagram. Essentially attach a header. So in this datagram, this is the data. header, data. The data is in fact another IP datagram. But from the routers in the internet perspective, in this cloud between the home agent and the foreign agent, a router doesn't look at the data, they just look at the header value, in particular the destination address. So we create a IP datagram inside another, and the outer header has a source address of the home agent and a destination address of the care of address. So we're sending now from x.z to y.m. So here we send that out across the internet. So here's our internet here. It's forwarded because of the destination is the care of address, that is y.m, an address on subnet y. It will be forwarded to the router that manages subnet y, which is our foreign agent. When the foreign agent receives this, it sees, okay, I just received a datagram. Source was x.z, destination y.m. It checks its visitors list. The visitors list should have an entry there that says y.m is the care of address for x.b. When it sees that, it realizes I need to remove the inner IP datagram from the outer one. That is, remove the outer IP header and send only this portion to the y.m, or our mobile node. So that's the datagram here that's sent from the foreign agent to the mobile node. It's the same as what was sent from the original correspondent node. We see the source is z.a, the destination is x.b. Our mobile node receives that datagram and it's received the data. Note, look at the source and destination addresses of the packets sent by the correspondent node and received by the mobile node. They are the same. Using the tunneling, correspondent node, source ZA, destination x.b. The datagram received here, source ZA, destination x.b. It's the same. If our mobile node was home, it would receive the same datagram. Source z.a, destination x.b. If it was in any other foreign network, it would receive the same datagram. So from the application's perspective, so the voice application running here and here, or the web browser, the addresses haven't changed. It's still x.b and z.a. But from the other network entities, the home agent and foreign agent, we use the tunneling to deliver from the home to the foreign agent. Tunneling is simply the process of putting one packet inside another packet of the same format. One IP packet inside another IP packet. So that's the three main processes for mobile IP. We need to discover foreign agents, we need to register with our home agent, and data is forwarded via tunnels between a home agent and a foreign agent. There are some alternatives that we can do with the tunneling in terms of how we use the addresses, but this is one common way. What about when we send back in the other direction? We create an IP datagram, source address z.a, destination address, source address x.b, destination address z.a. We send it to the foreign agent lets it go through and it goes direct or across the least cost path across the internet. It doesn't go via the home agent. So in the reverse direction to the correspondent node, there's no need to go via the home agent. because normal IP routing will work fine. It's only coming from the correspondent node to the mobile node. Yep.
When the mobile node wants to send a packet, some data back to the correspondent node, then it will use just a normal IP packet. And
Yeah.
what's the source and destination of that?
So it's the same as here. Oh, reversed, sorry. Data going from mobile node to correspondent node, we use our normal home addresses. We'll send to the router because we'd be configured to know that, okay, the next hop is this local router y.z. It's a foreign agent. Again, we've removed this security issue that normally, if we receive a datagram with a source address that does not match our subnet, this router, subnet Y, received a datagram with source X dot something. Normally, it would be configured to discard that, to throw it away. But because it's a foreign agent and knows that this one is visiting, it will let it through, send it out onto the internet, destination Z.A. The normal IP routing will deliver it to subnet Y, subnet Z, and eventually here. So it would go across the least cost path between mobile node and correspondent node. No need for tunneling there. And that's the basics of mobile IP and the main things that we need to go through and that you need to know for your exam. You should be able to, for example, given a scenario, work out the addresses, the source and destination addresses for different packets that are sent. Fill in the mobility binding table and the visitors list. That is, answer questions about which nodes are registered at a particular foreign agent or home agent, and answer questions about how the registration works, how the discovery works, and maybe even also some questions about performance. On the website and maybe in your handouts, I don't know, have a look, scroll, move. Do you have this example in your handouts? Go through. Yes, you have this example there. So in your handouts and online, there's a mobile IP example. Let's go through it, and it will just reinforce the concepts that we've gone through, just using a more detailed example. So it's on the website. I will do it on the board, or start doing it on the board so that we can show how things change as we go. In fact, in this example, we're going to illustrate the different mobile IP processes, and also using wireless LAN as an example, we'll go through the wireless LAN handover or the wireless LAN discovery. We'll get started today and finish next week, I think. We don't need this. Turn off, please. Okay. Easier. We have a example simple IP network. You've got it in front of you. I'll draw it quickly. I won't write down the IP addresses, you have them in front of you, but we have a set of routers, A, B, C, D, E, F, a correspondent node. This is attached via some Ethernet switch to a router, E, and we're going to have a mobile node that's going to move between two subnets. These are two wireless LAN access points. So this is one subnet. It's an Ethernet switch. Note that Ethernet is part of layer 2. From IP perspective, this is all one subnet. And so is this. And I think we're initially attached to access point 1. We'll treat this as one subnet. 1.1.1.0. We're assuming all subnet masks are /24, I think. That is, the first 3 digits in the IP address represent the network, the last one the host. We're currently attached to get started, to access point 1. We want to move to access point 2. That is, I've got my laptop, my mobile phone, I'm using Wi-Fi or wireless LAN. Associated with my access point 1, I've been transferring data, maybe as an example in a voice call, voice over IP call to the correspondent node, and I want to change to use access point 2. There are 2 scenarios here. One is that, let's say the 2 access points are using different channels. So let's look at the wireless LAN part of it first. This one's using channel 1. This one's using channel 6. Here's my mobile node. I'll remove our subnet. I'm close to this access point at the start. I've associated and sending data via here. I'm moving. And my signal's getting weaker from this access point, getting weaker. All of a sudden, I move to a point where it's too weak. I cannot receive anything from the access point. So in this case, if I no longer have access to my access point, the signal's too weak, I'm too far away, then I would like to discover a new access point. So I was associated with this one, signal's too weak, I get to some point, I cannot receive anything. So I would start some scanning to discover a new access point. I would change, because there's only 2 access points around. In fact, from the mobile node's perspective, there's only 1 now. This one's disappeared, it's too far away. I'm not receiving anything. I'm not receiving any beacons. I send a probe request, I will not receive any probe responses because access point 1 is too far away. And I will not receive anything from access point 2 because it's on a different channel. Okay, they're on different channels. So I need to start some scanning process to check different channels. My wireless LAN device will now start trying channel 2, channel 3, channel 4, and scan through the channels to try to discover a new access point. We did that in the demo yesterday and last week, that we can run a scanning via the command line to show all the access points nearby. Basically, it rotates through the different channels, sending probe requests, hoping for probe responses. So, mobile node, once we lose connectivity here, we start scanning. When we get to channel 6, let's say I send a probe request, I should receive a probe response. And then I've discovered this access point. And I'll choose to associate with it. That's one scenario where the 2 access points use different channels. What about another scenario? They use the same channels. In this case, what may happen is that my mobile node, I'm originally associated with access point 1. I'm sending data. As I move, I notice the signal getting weaker. Okay, it's getting weaker. I'm also on the same channel as access point 2, so I may start receiving beacons from access point 2. I'm not associated with it, but I'll still receive those beacons. And the implementation of my wireless LAN device would have some algorithm to make a choice to hand over between access points. I'm continually receiving beacons from now 2 access points. And in fact, also data from access point 1. So one algorithm may be, okay, if I receive 3 beacons from a new access point, which is 10% stronger than the old access point, let's hand over. Or we can have a similar type of algorithm. Some algorithm that allows my mobile node to decide to use a new access point. So as I get closer, the signal gets stronger. At some point, I'll make a decision. Let's change from access point 1 to access point 2. And when I make that decision, I'll associate with access point 2. Authenticate and associate. Authentication request, authentication response, association request, association response. This is just wireless LAN handover, nothing to do with mobile IP. But if we're using wireless LAN as an example, this must occur before we do the mobile IP handover. So before this, I was sending data via access point 1. I discover AP2 is better, so I do a handover. So I'm now associated with AP2. I need to discover the foreign agent. AP2 is in a different subnet. I need to discover the foreign agent. One way may be that when I perform the wireless LAN handover, so I'll continue this diagram here. I actively try to discover a foreign agent using a router solicitation. That is, I create a special IP packet, an ICMP packet that is called a router solicitation, and I broadcast it to everyone on the subnet, which means I send it to the access point and set the destination IP address to be the broadcast address. For example, destination all ones address. So this IP datagram, destination address, which means everyone on the subnet should receive it. I don't know what the subnet address is yet. I know nothing about the IP address structure of this new subnet. I've just associated with the access point, so I send a router solicitation. There may be other hosts that receive it, but one that will receive it is router F, which, if everything's working, is a foreign agent. If that's the foreign agent, then router F will respond with a router advertisement. And in that router advertisement, I learn the IP address of the foreign agent. In figure 4 in the diagram, in the handout, you'll see that structure of that router solicitation. It's an IP datagram which contains an ICMP packet, the source address. My mobile node didn't have a source address from the perspective of this new subnet, so we use that special case all zeros source address. And we want to send to everyone on the subnet, so we use a special case all ones. 255, 255, 255, 255. That's the router solicitation. And then the router responds, and it's in figure 5 with the router advertisement, with the source is the address of the router, destination. Because I don't have an IP address yet, it broadcasts this router advertisement. So this is figure 5. And inside this IP datagram is an ICMP packet. And one thing that includes is the router or the foreign agent address. And in our example, the foreign agent and the router are the same. Therefore, we get the same address. So we've now discovered a foreign agent. And we've actually, the first thing we do is we discover an access point. And depending upon the scenario, if they're on the different channels, we need to effectively lose connectivity with the old access point and then scan and associate it with a new access point. If we're on the same channels, we can be a little bit smarter and choose a new access point when the signal meets our requirements, or that we have an algorithm to choose which one's better. And once we choose the new access point, we associate with it with the normal wireless LAN mechanisms. And then we need to discover a foreign agent. And in this example, we send a router solicitation to everyone on the subnet, and a router, which is acting as a foreign agent, responds with the router advertisement. And after that, we now know the foreign address of the router, the foreign agent. The next step is to register. We'll continue that and go through that rest of the example next week. But you can read through. It's given there in detail of the packets and a description. So have a look at that. We'll go through it quickly next week and then touch upon mobile networking.